I'm really happy to be here talking to you today about water potential. I hope you had the opportunity to watch Dr. Doug Kobos's Water Potential 101 talk. I did, and I thought it was great. And I hope it took you through and helped you understand a lot about the fundamental principles of water potential. Because today, even though I love the topic too, we're not going to have time to go back and look at any of those things. So if you haven't watched it yet, it's available on our website. Go ahead and watch that and then look at this, because we're going to go into more advanced topics on water potential. We're going to talk about choosing the right instrument to measure water potential. Essentially, we're going to go through two parts. The first part is measuring soil water potential. Now, if you look at the things we're going to talk about here, we're just going to go through all the instrumentation that you might use to measure water potential in the lab and in the field. And I hope that once we're done with that, you'll really understand what you need to do to make those measurements that you'd like to do for your research or whatever it might be that you're using water potential for. Now, there are basically three types of measurements we're going to talk about. Is it an exhaustive list? No. There are other techniques. I'll even mention a couple later on. But really, these are the techniques that we use. These are the things that I've used in my own research. And these are the techniques that most labs and most research around are actually using. So these are the ones we're going to talk about. And maybe at another time we'll get a chance to go further into depth into some of these things. But let's kick it off. We'll talk about solid matrix equilibration techniques first. And then we're going to go on, talk about liquid equilibrium, and finally, vapor equilibrium. Now, to understand solid matrix equilibration sensors, we got to understand exactly why they exist and what we can do with them. All of these sensors don't actually measure water potential directly. They measure something that they can measure very well, and it happens to be water content. That's a pretty easy measurement to make. And they infer water potential from that measurement. So we start up at the top of our slide with measuring water content. And we do this in a matrix that does not change. As Doug told you in the first seminar, he said that anytime a matrix changes, then we have a different relationship between the water potential and the water content. So we need to keep that matrix the same. So we developed this soil water characteristic curve, something that Doug talked about last week, and a series of words I'm going to say multiple times through the seminar. We often abbreviate that SWCC. We create that for our matrix. We start then by measuring the water content. We come over to this relationship line that we've created right here in the middle. Go down to the water potential. If we know this relationship, we can then measure that water potential, and eventually we get out of the sensor something you never see if you use them, this apparent soil water potential, which is what we wanted to get in the first place. But it all comes through this relationship, the soil water characteristic curve. Now, there are several sensors out there that you can buy to make this measurement, and we're going to talk about three of them here in this presentation. The first one is the electrical resistance method for measuring water potential. What this does, like all the sensors, it equilibrates a standard matrix with the surrounding soil. I've got an example there. If you look here at the bottom of the screen, you can see the soil, or what I've tried to make look like the soil. The sensor gets put in the soil, kind of pressed in there, and we hope that the water in the soil will move across that white fabric you can see on the sensor I've got pictured there into the sand matrix, through the sand matrix up into a little white capsule there I've labeled the gypsum capsule. That gypsum capsule actually contains two electrodes, a plus and a minus, and we measure the resistance across those two electrodes, and that resistance across a known matrix that we already have figured out using the last slide's relationship, the water content to water potential, we are able to infer the water potential of the soil. The good thing about these sensors are that they're quite inexpensive. You can pick up a lot for not very much money. But one of the problems with the sensor is that, like any of the matrix sensors that we'll talk about, these solid equilibrium techniques, you have to have good contact with the soil to make sure the water flows in. If it doesn't flow in, our measurement is useless. Another problem we have is that inside that sensor, there's sand. If we're dealing with a clay out in the bulk soil, we have a poor connectivity challenge just based on just basic soil physics. And if we don't get those matrices consistent, the gypsum blocks that we're measuring in, those chunks of gypsum, if they're changing in their pore size distribution, they can create a different soil water characteristic curve, and then we don't have the relationship that we want. Now, some of these things actually go for the three types of sensors we're going to talk about, so I'll try to point that out when that's the case. The next one we're going to talk about is the capacitance method. Now, in a very similar manner, instead of the gypsum being the matrix that we're measuring, now we're actually going to measure the ceramic, a ceramic disc. These ceramics have been designed and perfected over the last 30 to 40 years, and I do mean that. In soil physics labs everywhere, people have been trying to come up with the greatest ceramic they can find, that every time they mix a batch of this together, that it comes out with the exact same pore size distribution, i.e. that SWCC is the same for each one of these ceramics. If that's true, in this sensor, we measure the water content using a capacitance technique or a charge storing ability of this ceramic. We measure the water content, and then we define that relationship between water content and water potential. And again, just like we've talked about with the first sensor, we get an apparent water potential of the soil. Now, one of the nice things about these sensors is because they're made out of ceramic, the stability of that ceramic compared to a gypsum is quite good. It survives in the soil for years and years, and that's really important. And a lot of tests on these type of sensors haven't shown much salt sensitivity either. One of the limitations of the sensor, and something we're going to talk about that we really find in the measurement of water potential, is it doesn't operate over the entire range. You can see at the bottom of the slide right here, it only measures from about negative 0.01 megapascals, so not zero, not completely wet, to negative 0.5 megapascals. So that range includes a lot of the plant usable range, but it doesn't quite go all the way wet, and it doesn't quite go all the way down to permanent wilting point. And this is a challenge for all the sensors that we're going to talk in the solid matrix equilibration discussion. The third sensor on that list we call a heat dissipation probe or heat dissipation sensor. This heat dissipation sensor actually uses the exact same ceramic, this one developed in the lab over these years, to measure the water potential. But it's different because instead of using a capacitance, a charge storing technique to measure the water content, it uses a needle that measures the thermal conductivity of that ceramic and relates the thermal conductivity, which is approximately a measure of water content, it relates that thermal conductivity to the water potential of the surrounding soil. And you can see that there. The sensor that I'm showing right here, you have that blue line that you can see, that's essentially the heating needle inside there, and that heat just dissipates into that ceramic. If it gets wetter, the thermal conductivity goes up, and we can make that relationship of water potential. One of the cool things about this particular sensor is that it can measure across a broad range. Most of the way wet, although it struggles as you get very near saturation, to all the way dry. In fact, in one of the papers that's been published on this particular sensor, they show it operating in air. They can actually sense the relative humidity of the air, which is pretty cool. And you and I think, would agree on the point that that is very dry. So that's pretty interesting about this probe. One of the downsides about this sensor is that, in fact, it takes some pretty good work to get that calibration done. First of all, it takes a complex temperature calibration, and according to the papers that are out there and trying to buy these sensors, you need a individual sensor calibration. But never fear, if that's not something you want to take care of, it's not something you want to do as a part of your research, there are companies that actually do this calibration for you. So that is a possibility. Let's step away from our solid matrix equilibration techniques and move into the liquid equilibrium techniques. There's only one of these. It's the tensiometer. And it's one of my favorite devices to use in the lab. The tensiometer is an interesting sensor because instead of our solid equilibrium, which requires a conversion from water content to water potential and relying on that relationship, the tensiometer is a direct method of measuring soil water potential. Why is that? Well, just look at the slide up here. What we have is a tensiometer there. You can see a little column and a little white tip at the end of that column. That column is filled with water. That tip, the white tip, is actually a permeable ceramic that allows water to freely flow into the tube and out of it. That tube is capped at the end, so there's no opening to the air. Instead, at that end, there's a pressure transducer. And when you stick it into the soil, assuming it's not at zero water potential, not at saturation, is actually, depending on the water potential, going to suck water out of that column. And because it's sealed on the other end, the pressure transducer can measure that pull of water, and we can get a direct reading of water potential in the soil. So why don't I stop my presentation now? Because we found the best way of making water potential measurements. That would really be easy, except for the fourth bullet point down there, which says our range is from 0, which is great. We go all the way to saturation, but the lower limit is negative 0.09 megapascals. That's not even quite out of the plant optimal range. It's great to use across that range, but when the suction in the soil, when the water potential sucks, I guess I would say, so hard on the water column to go beyond that value, we create air bubbles in the water column, and then this technique breaks down. And the final point on the slide where we say significant maintenance required, that is what I'm talking about, because you have to go in and you have to refill these tensiometers with water and put them back out in the field or in the lab. And this actually takes some time. So great technique, has its limitations. We just need to know about them. We can deal with them if we know what they are. Our last set of measurements that we're going to talk about before we get into some fun stuff in the applications is vapor pressure measurements. Now, vapor pressure is an interesting topic, and I would love to go into it in more detail here, but here is really a time where if you didn't catch Dr. Kobos's talk on the Water Potential 101, you really need to go back and look at that, because he showed that there's a relationship between the relative humidity in the air above a sample or above a soil, let's say, maybe in a machine above a sample, and the water potential of that sample. And I'm not going to go into the details here. It's cool stuff. Go watch Dr. Kobos's web seminar if you haven't seen it, and then you'll be ready to talk about that right now. But here we go. When we equilibrate this above a sample, if we measure the relative humidity, we can actually determine the water potential. And this is also a direct method, just like our tensiometers were. Now, there are two basic methods. They're using the same principles. They're both trying to measure relative humidity. One is doing it through the wet bulb technique. The other is doing it through a chilled mirror dew point technique. And I'm going to briefly describe how each one of these works and look at the instrumentation available to actually make these measurements. So first, a thermocouple psychrometer. This is one of the grand old men of water potential measurements. It was done, it's maybe one of the heydays of thermocouple psychrometer, really was back in the 1960s. There was a lot of work done, there's a lot of really interesting work done, and if you want to go look in the literature, you can find out a lot about this technique. We don't have the time to do that right now, so I'm just going to briefly explain what it does. We have two dissimilar metals joined together to form a thermocouple. Why do we want a thermocouple and not just some thermometer there? When we make this temperature measurement, we have to do it extremely accurately. We don't have the choice to just go put a thermometer in there and guess at, maybe a half a degree C. We're talking 1/1000th of a degree C. And so a very small temperature sensor is required. The only thing that can really do that is a thermocouple, and maybe there might be another technique to do that now, but certainly that was the best one back then. And what happens is we take this thermocouple, this very small temperature sensor, we cool it down using a voltage that we move through there. When it gets cooled down, water condenses on that thermocouple, and then we stop the cooling and just leave it sit in the air above the sample. What happens then is that the water evaporates from the surface of that thermocouple, and the evaporation of that water causes the thermocouple to cool, and the cooling of that thermocouple will drop down eventually to this thing we call the wet bulb temperature. The cooling that would happen as water evaporates into air and takes energy from the surface of that thermocouple. So that's what's going on there. Because it's a thermocouple and we can measure the temperature accurately, we can actually make a measurement of the water potential. There's a couple of different devices that do that, but like I say, this is old technology and it's not really being developed currently. This is an instrument actually that is made by a company called Westcor. This is a soil psychrometer. It's really the only way I know of to get thermocouple measurements, wet bulb measurements in the soil. What you see on this slide is a soil psychrometer, the little silver bead below that red cap. That's the thermocouple. The size of the wires you're looking at there, size of a human hair. So we're talking about very, very small device there. This is, on your computer screen, this is many, many times bigger than it actually is. These get buried in the soil. They get hooked up to that instrument there, which is a readout device. This thing has to be able to resolve voltages into the nanovolt level. So we're talking a pretty good piece of instrumentation. You can go out and measure your soil water potential. Well, one of the challenges here with making this measurement, and I've done it many times myself, simply temperature gradients. If we're trying to measure temperature to 1/1000th of a degree, sticking one of these things in a natural environment where the temperature is changing a lot, that plays havoc with the measurements. And you're going to have to take some time to be able to get really good measurements out of this system. Another instrument that's out there is a thermocouple psychrometer that's in the lab. This does it a little bit differently than I just showed you. This has a big chunk of aluminum that you put samples in those little sample cups that we're showing in the picture right here. When that soil gets in the sample cups, you put them in the round device there. That is a big chunk of aluminum and allows the temperature in there to reach isothermal conditions. And then you use a thermocouple psychrometer to actually measure the wet bulb and get to the relative humidity and therefore the water potential. This is great. It actually worked quite well. The range was about 0 to -6 megapascals. Drier than that, we couldn't cool water and have it condense on that little thermocouple bead. But it's limited actually up in the upper range to about 0.1 megapascals. That doesn't even resolve anything in the plant optimal range. So you can see this really isn't something we'd, for example, use in your garden to go collect samples and figure out the water potential there. Now, stepping forward, technology has gotten better and better over the years and good enough so that we can actually make this measurement not with thermocouple psychrometers anymore, but with chilled mirrors, which have a big bonus to them that it takes far less time. The measurement I just showed you on the last slide, you have to wait at least an hour, usually 2 or 3, to start making measurements for that thermal equilibrium to take place. One of the steps forward that has been made in this chilled mirror technology is that we measure the sample temperature directly. That way we don't actually need total thermal equilibrium to make this very, very accurate temperature measurement. But how is this done? So I'm showing a picture here. On the far side, we have the infrared sensor that's measuring the sample temperature. We have a mirror that's labeled there. That thing cools above and below the dew point temperature. And that optical sensor on the other side senses the dew point temperature, and then very, very accurately. And then we can therefore get our water potential from that dew point temperature. Now, one of the steps forward that's been made is this instrument now can measure accurately that thousandth of a degree, which is extremely important in making water potential measurements up at the high range, meaning near zero. But even with its ability, as we'll talk about a little later, the accuracy is still limited to only some in the plant usable range. But we'll get to that, don't worry. Now, the instrument out there, really there's only one available to make this kind of measurement. It's a chilled mirror dew point hygrometer, or potentiometer. Range is about 0 to negative 300 megapascals. And as I said, the accuracy now is half what that thermocouple psychrometer was, but still it's 0.05 megapascals, half of the kind of plant optimal range, which I think is about 0 to, a little less than 0 probably, to negative 100. As I said, the great news is that this technique, the chilled mirror technique, can actually make a measurement in 5 minutes to say 15 minutes, where the old thermocouple psychrometers, you could go and have lunch and do a couple other things before you actually make measurements on that one. So let's talk just briefly about some important points that we've already covered in part 1 of this discussion. First, there is no one ideal measurement for water potential. That's unfortunate. I'd love to end my career in working in this area by saying, now we finally figured it out. We've got something that measures all the way accurately from 0 up to negative 300 megapascals. That'd be great. So far, it's just not there. There are great choices out there available for covering the range, both in the field and in the lab, but you're going to have to pick and choose to get the right range that you want. One of the things we're going to learn in part 2 is that techniques can be combined, and they must be combined, to get a complete understanding of water potential across the entire range. So let's jump on. Let's talk about part 2, applications of soil water potential. I'm going to spend the majority of the time now that we're going to talk focusing in on soil water characteristic curves, or soil moisture characteristic curves, whatever you want to say. We're going to spend a lot of time talking about that. Why? Because most people who are making water potential measurements actually want the SWCC, and they want it for a variety of reasons, only a few of which I put up here. Some people are using for plant available water. Some people are using them to look at soil surface areas. Other people are doing swelling soil analysis with this. We'll talk about how to get there in just a moment as I take you through actually creating one of these SWCCs. Now, that's not the only measurement, because we know ideally if we had a very good method, inexpensive, very user-friendly, we love to make water potential measurements in the field. And we'll talk about some options there. Are we there yet? A headache-free measurement of water potential in the field? I don't think so. We're still working on that. But, you know, with time, I think we may get there. Some of the other things we might be able to look at through water potential is water flow and contaminant transport. If we know something about the water potential at the spatial distribution of water potential in our soil, we can do a lot with our models to consider where the water is going in the soil. And finally, something that some of you may be interested in, using water potential in irrigation management. Something that's not done a whole lot these days, but there are some options, and it may be a great use of a great use to you. So let's jump in. The soil water characteristic curve, or SWCC. Doug talked quite a bit about this in his web seminar just a few weeks back, and I'm not going to try to dive into this too much again. Just want to preface our discussion because he didn't talk about how to measure it, and I'm going to do that. So let's just recall what this was. It's again the relationship between soil water content and water potential. And that relationship is different for different soil types. And we're going to see this. We're going to show you some data that we collected in our lab on a lot of different soils and show you how it changes for these different soils, and maybe briefly just mention what effect that might have. Now we're going to go through these determinations in a little bit of detail of things like plant available water, surface area determination, and finally looking at swelling soils, which may not be even your area of study. But to me, when I learned more about that determination and what you need to learn about that, I was really excited to learn, because I lived down in Texas for quite a while. We have shrink swell clays down there where I lived, and it was interesting that a lot of foundations were being torn up because of this problem with swelling soils. And using this technique of SWCC analysis, we can actually determine beforehand, before we ever build on that soil, if it's going to be a swelling soil and what we need to do to mitigate those effects. I had a friend whose house cracked completely in half. They probably wish they had made that measurement beforehand. So let's jump in. Let me give you a little background about the experiment that we ran in our lab. We're going to talk about some history here, because it's important to kind of put this in perspective as far as the options you could use. Now, I show a couple of different arrows on the near side of the slide showing one technique that we can get water potential that we didn't talk too much about. We're going to talk about it now, and then something you recognize from the talk earlier, and then kind of the ho-hum water content. I'm sorry for all of you who measure water content. I do all the time, but it's just not quite as complicated as water potential. So let's talk about that. Now, filter paper. I showed it in the last slide. It's a pretty common technique of measuring water potential in some areas. Now, it's been around a long time. Let's rewind the clock back to the 60s, the 70s, and 80s, when the only technique for measuring dry soil water potential really was this thermocouple psychrometer that I talked about. And I kind of mentioned it there, reiterate it here. It was a difficult measurement to make. What people did was said, well, I don't have hours to wait for my thermocouple psychrometer to equilibrate, not getting the accurate numbers like I really want anyway. I want to do this once with something I know about and create the SWCC of the filter paper. Okay? Then I can put filter paper in contact with my soil, allow the equilibrium of this filter paper, then weigh, dry weigh, or get the water content of the filter paper, and then use the soil water characteristic curve to relate the water content that I measured on the filter paper to the water potential. This was an idea. They calibrated using some of these original techniques that I talked about. The pressure plate, which we'll get to in a moment, and the thermocouple psychrometer, and got this information to give them the SWCC. This is great. Then the labs can grab hundreds of soil samples, put filter paper in many of them, and they had to define many things about this filter paper. Wattman 42 was a common one they used. And they put this filter paper in and started making water potential measurements. Well, there's a challenge. Problem with this measurement. The first one is that this SWCC that has been defined classically in the articles I'm kind of showing up top there, that you can go look at if you like. Some people are finding they just didn't fit. As they went back and reviewed the data or reviewed their own data on the SWCC, they found that the filter paper that they thought, when they ran this relationship, they thought they were getting a particular water potential, but they were getting something quite different. And that shouldn't surprise you based on our discussion of these matrices, because if the filter paper matrix changes at all, it changes the SWCC. There were other problems. Equilibrium time takes 7 days at least, if it's even equilibrated at all. Hydraulic conductivity, when you put it in contact with the soil, are we in equilibrium? And even some of the techniques these days include kind of putting a filter paper across a membrane with the soil on the other side and waiting for vapor equilibrium. That's even more dangerous and difficult to do. Other things that cause problems. After a while, you get fungal growth on the filter paper, which is a bit of a problem. You can see that there are many challenges. Now it goes on being used. It's a technique you can get water potential from, but in my opinion, there are better techniques, and we'll talk about that. Another technique that was used in this system, you've got the filter paper on the dry side, you've got your pressure chamber on your wet side. And this was introduced way back in 1930 by L.A. Richards. We equilibrate a soil sample right there on a ceramic plate. We put the top down on the pressure chamber you're seeing on the far side there, screw the screws on tight to make sure it doesn't blow up, and then pressurize it. The only way for water to get out of the system is through the ceramic, out a tube, and out to the atmosphere. Wait some time and measure your samples, and you got your water potential at that particular water content. A good way of making your SWCC. However, there were some challenges here too. First of all, making measurements on wet samples, by the way, that's fine. Dry samples, the equilibration time is extremely long, from 1 week possibly to never. And recent papers that have been written have shown a real difficulty in even equilibrating the pressure plate at these very low water potentials at pressures from 500 to 1500 kilopascals. Now, if your sample never equilibrates, your water potential is not going to be correct, and therefore your SWCC is going to be off. And this is a big problem. There's a little reference there at the bottom of the slide. We can talk about that at the end of the presentation if you have questions on that. There are even more recent references on that, and we can certainly get into that then if you'd like. Before we go on, I want to show you something, and it'll be interesting in the results that we get. I'll point it out again, but I'm showing you a little poster. You can actually order one or get one of these from Decagon. We give them out free if you're interested in putting this up on your lab so that you have this information there. But we go through on this poster and just talk about the many techniques to measure water potential. If you look at it here, you have pressure plate, you got HYPROP, we'll talk about in a little while, I haven't mentioned that. You got the dew point potentiometer, the granular matrix sensor, which we talked about, the electrical resistance, that's the granular matrix sensor. Heat dissipation we talked about. The MPS1 is that capacitance type sensor, the tensiometer. All our gentlemen are there that we talked about already. Now I show through there what I call the no man's land of water potential instrumentation. It really lasts from a little past 100 kPa up through about 100 kPa to 1.2 megapascals, negative 100 to negative 1.2 megapascals. So this is the area that I talk about as being the no man's land. If you look at that poster carefully and look down at how that shading, you realize that in that area we don't have any really good measurements. And that's a bit of a concern. Some of the technological advances we've had actually have helped that. I'll talk about that in a minute. But you can see that no matter how we slice it, our water potential instrumentation do not adequately cover the entire range with good accuracy. So that's an interesting poster. You may want to get a hold of one of those so that can sit on your lab wall for your use. Now, choices to make these SWCCs. We didn't choose a pressure plate and filter paper because those technologies to us really have been improved upon. What we did in our lab to make some SWCCs is, for the wet region, we talked about a tensiometer, and we're going to show you a little bit about what we did with that. We also used a new technique that's fairly new on the market called the Windschindler technique, which is an integrated tensiometer with an intact soil core that sits on a scale, and I'll describe that measurement just a little bit more to you in a moment. Now, this isn't really a new measurement of water potential, but it is a new technique that integrates some of the things we already know into a new way of doing things where we're actually using these techniques with a bit of modeling to come up with a better answer. For the dry side, we used a vapor pressure equilibrium technique. Like we used the dew point potentiometer because that really does cover the dry range quite well. And we're going to do a little evaluation of how did these fit together. What are you going to see when you do this in your lab? But first of all, let's just quickly look at the measurements again. We already talked about that the tensiometer, that in fact, yeah, it equilibrates with water in the soil. We measure the pressure, the negative pressure of water in that column. We already described that accuracy. I need a minus sign on that slide over there. It's actually negative 80 kPa, not plus 80 kPa. That, of course, would be pressure. And we need to measure this actually in a undisturbed sample. We have to have a representative sample in most conditions. If you're in geotechnical engineering, of course, you're going to repack samples anyway. They're going to be compacted, so it may not be a big worry. But in soil science, where you're getting the natural soil there, you have to pay attention to how you sample the soil, because you don't want to create a sample that's outside its natural condition. And with one of those soil rings that we're showing in that picture over there, you can actually sample a natural soil there. Now, if we could use the tensiometer, we already talked about that. The SWCC can also be analyzed in the wet region by using this Winn-Schindler technique, and I show it here. Now, look on the near side, we've just got a couple of tensiometers sticking up out of a base. They're at two different heights. What we do is take our soil sample, we put that soil sample onto these tensiometers and allow that soil sample to dry into the air. And we monitor the water potential over time to see how that changes as we monitor the weight on that scale. And using this technique, we can create the SWCC for wet soils. What do you do for dry soils? Well, this is our old friend. We've already talked about it, the dew point potentiometer that we collect the dry side water potential in. But notice I didn't say water content. What do we do from that? Well, to prepare our sample for that, we typically take some kind of bottle. We've found some baby food jars. You can use anything that will seal. Take our soil and we typically wet it up. Now I'll tell you where that becomes a problem now in a minute, but this is our standard method. We also have a application note on our website. You can go in and look at that if you like. We wet the soil, we mix it, we let it stand for 24 hours, and then we put it in our sample cup. Now you say, wait a second, you just mixed the soil that in the last couple of slides you said needed to be undisturbed. Most of the soil samples, most of the water potentials that dew point potentiometer can measure are actually so low that it doesn't matter to disturb the larger pores in that soil by mixing, that it doesn't matter when you do that. But I'll show you a point now that instrument is good enough at this point where that may become a problem. Rating the sample is simple. We already talked about that. You grab your sample, put it in there, turn the knob, and you get a reading in 5 to 20 minutes, depending on how wet your sample is. Now I'm going to show you the results of one of our experiments that we've actually done with this setup to show you what we found. Now these are the type of soils that we had. I don't have time to go into detail. They're all on the individual slides, but we went all the way from a sand all the way to a silt loam, and even threw in some volcanic soils there for some interest. Right there at the bottom, notice their bulk density is down around 0.5 or 0.6. So that's kind of interesting to see what happens there. So I'm just going to take you through a few of these SWCCs for these different soils, not to get in depth about what we're talking about, to try to understand what the particular results mean to us in terms of the knowledge, but just show you what you might see in your laboratory. I don't have time to actually delve into it beyond that. So the red points we see here were just tensiometer. We didn't actually use the Winn-Schindler technique on this particular experiment. When we were done with the water potential analysis, we actually sampled the soil, put it in the oven, or weighed it, dried it, and weighed it, and that's where we collected the water content data. Nice thing is, on this sample we see some interesting things that we want to see if they continue in the rest of our measurements. The WP4, that's the chilled mirror measurement, and the red, which is our tensiometer, those guys matched up well, and that was pretty exciting. that we were able to actually cross that no man's land with this measurement. Did it happen every time? Well, that's really what we wanted to know in some additional tests. Here's another volcanic soil. Those are fairly similar soils. We weren't surprised to see we got a consistent relationship. And we were really happy that we could fit it with an equation to give us this relationship in our SWCC. Okay, now we're going to step up a little bit. For the wet side now, we're not using the tensiometers. We're actually using the Wynne-Schindler technique. What you notice here is that we can produce a lot of points with the Wynne-Schindler technique and really define that curve, which is pretty exciting and help us with curve fitting. We've changed the water retention curve relationship from the Campbell-Shiazawa now to the Van Gnuchten equation. Why? Just different way of fitting it. Now, in these data, what we see is, once again, we matched up fairly well with the chilled mirror and the Wynne-Schindler technique now this time. And we're pretty happy with these data. But yeah, this was easy. We did it on a loamy fine sand. People have said that soil physicists always want to work in sand because it's simple. And I think that's probably true. But in this case, we better talk about a little more fine soil to make sure this works across the region that we're interested in. Here's an interesting one. This is a Kiona fine sandy loam. You notice a bimodal distribution here. This is quite interesting, but very representative of some soils that contain a rather widespread pore size distribution that may be pretty heavily in the large pores and the small pores, and maybe not necessarily in the middle. So what we're seeing here, it's a little bit harder to tell. Do we match up? I'm not really sure, because we could have thrown that. You see that triangle? That's actually the cavitation and emptying point of the tensiometers in the Wynne-Schindler technique. It's stuck out there, it's nice, but do they really match up? Well, let's go to one more slide to make sure this happens. This looks pretty good. Now we're doing a pellucid loam, nice fine soil, and we do get pretty good agreement. And we were pretty excited about this slide until we looked up there, and look in the middle of this slide. We have all the squares from the dew point measurement heading off out into the middle of the slide away from the Wynne-Schindler technique. And we thought, what is going on there? We now have the ability to measure near zero with that dew point measurement, but are we off base? Are we missing something here? We went back and looked at what we did, and in fact, you know that the Wynne-Schindler technique, I told you, and if I didn't, I meant to, that we saturate that sample and dry it down. All the dew point measurement samples, as I told you before, our technique is to wet them up. And in fact, those data were caused by hysteresis, and differences in the wetting and drying. When we changed around and actually started with those samples for the chilled mirror, saturated or very, very wet, and dried them down, they fell on the curve, which is really interesting. But you ought to think about that for making your own measurements. Okay, so what can we do with our SWCC? I already talked about this: plant available water, surface area, swelling soils. Let's get right to it. Plant available water, we've talked about this quite a bit, but you're seeing an SWCC for a couple of different soils run in our lab. One was a sand, one is a clay. You can see how very different those are. But we can go ahead and see what the water content is at permanent wilting point and field capacity, and we're going to get back to this analysis in a little while, where I talk about bridging the gap to our field measurements of water content. So hold on just a second. Some other things we can do is, with our SWCC, we can take a relationship between the semilog plot of an SWCC and a technique called the EGME method for looking at soil surface area, and we can relate the two. And instead of using this EGME method, which is pretty difficult, we can actually just create an SWCC and get our soil surface area, which is pretty cool. Another thing we can do, and I mentioned a little bit earlier, talking about swelling soils and having your house crack in half. Bad thing. We can use our SWCC and plot the suction in PF. Now, I'm not going to go into what all this means. It's basically, the PF is just a log-based log base 10 of the water potential starting at 1 centimeter of water. If you watched Dr. Kobos' presentation, you know how to convert those. So if you do that and now plot the suction of the water potential, suction is what they use in geotechnical engineering, and it's the negative of water potential, and you relate that to the water content, the slope of that curve, let's go ahead here, the slope of that curve we can put in this table from McKean in 1992. And the less negative that slope, the more swelling potential that soil has, and the more special consideration it will need if we build anything on it. Now, let's jump into a couple of other applications before we finish this. We're running short on time, so we got to just move on. What if you're wanting to measure the water potential of soil in the field? What choices are you going to use? Well, I kind of threw up a few. There are a few choices you can get at, but generally they are related to our solid matrix equilibrium techniques that I talked about first. Why? They're inexpensive and they require pretty low maintenance. If you're wanting to monitor year-round water potential in the soil, from wet to dry, and that's pretty much what soils are like out there in the environment, your solutions really center around heat dissipation probe, soil psychrometers, although I did point out that would be a pretty big challenge, or capacitance matrix potential. Those are your choices you have. You can make pretty good measurements using those. A lot of people also use tensiometers, but the big concern is they are a maintenance headache. However, there are tensiometers out there that have been developed that can go to very high or low water potentials, more negative water potentials. So you can go out there and look for those. They're not very common and really more in research university labs. And there are tensiometers out there that will self-fill. So when they go dry, they'll wait till the water is back in the soil, they'll sense that and fill themselves back up. So that is an option. Contaminant or water flow and contaminant transport in soils. You're out there trying to make measurements of potential gradients so that you can put them in the model and try to figure out where the water is going and where the contaminants are going. There are some good solutions out there. Typically, when we talk about this, we think about this in terms of pretty high water potentials, pretty close to zero. And the reason is that really water flow and contaminant flow typically, the vast majority of that happens when the soil is pretty wet. So really a tensiometer may be a really good option in this case. Although maintenance is always going to be a question that you're going to have to focus on. Another possibility is a solid matrix equilibrium sensor. Got to remember though, most of these sensors do not operate very well close to saturation. That's where a lot of the flow is going to go. You're going to miss it in your analysis. And finally, another option, irrigation management. Trying to control your irrigation, sometimes deficit irrigation, sometimes just to get the optimum value of water potential for your plants over time. Our range when we irrigate typically is about 0 to negative 100 kPa. I already told you that was kind of my opinion of the plant optimal range. If you're going to or past negative 100 kPa and you're not trying to do some deficit irrigation, you probably got some problems. So maybe a good choice would be the tensiometer. But you also have the granular matrix sensor. One of the good things about those, they're pretty inexpensive, so you can put a lot out there. Another choice, heat dissipation probe or the capacitance probes. All of those things that we talked about early on. Well, we've reached the point where we can quickly bridge the gap from water potential to water content. I mentioned this a little bit earlier. We had a field experiment where we were measuring the water content with some probes, really easy to install, covered the whole range of water content, of water in the soil essentially. But we wanted water potential. We wanted to understand why the plants were taking up water, why they weren't, what conditions were out there that would create these interesting little things that were happening in our particular research site. So we decided that we would break through this conventional myth that these SWCCs are time-consuming and not a great way for this analysis, and we went out there and took our water content measurements that I'm showing on the near graph here in the color at the top, went through SWCC that we created in our own lab, and then converted our water content measurements into what we really wanted, which was water potential. This actually told us some pretty interesting things. I can't go into it here, but essentially it told us why the plants were stopping taking up water at the various levels in the soil that we buried these sensors. And so for you, this may be a great option to measure water content in the field and use an SWCC to bridge the gap to an understanding of what we typically want to know, which is that water potential relationship. Let's finish up just talking about part 2, important points on the application of these water potential measurements in your research. Water potential measurements can solve a lot of problems. I hope after this discussion of applications, you can see there's a lot of places you can use it. And heaven knows I didn't cover even nearly all of the things that you might want to be doing. You got to be careful though making these measurements, because getting the right data is not just simply a matter of going and taking one of these instruments, putting a sample inside it or putting it in the ground and just wait for the data to drop in your lap. You got to understand what you're doing. I hope this seminar series will really help you get to that point. And finally, correct measurements of water potential can lead to important knowledge about your system of interest. If you do this correctly, you can really understand, you can begin to model systems and create an understanding of things that we simply don't know. And I wish you all the best in your research into water potential and other topics.